Okay, so in nth order, we're going to have a theory of solutions today. Whole bunch of just notes today. If we have an nth order linear DE, it'll look like the nth derivative of y with respect to x, some function of y, or some function of x, call it gn of x, plus next derivative down, all the way up to the first derivative, g1 of x, plus, I'm running out of room there, the 0th derivative, which is just regular old y, times some g0 of x, equals over here some function of x. This is nth order because our highest derivative is n. It's linear because all my functions of y here are to the first order. In fact, really the only function of regular y is right here, and it's just y to the first. And then we have y prime to the first, y double prime to the first, and so forth. Now, this is the most general kind. These in general are very, very difficult. So the kind we tackle first would be what are called with constant coefficients. So all of these g's are constants. They're just numbers. Gi is just some, let's call it Ci. We say one of these DEs is homogeneous. Remember, in first order DEs, the word homogeneous means something different. I left out letters there. If this guy over on the other side is 0. Okay, so for example, let's write up one. Let's say we have the 4th derivative of y times 5 plus 3, third derivative, plus 17, the second derivative. Maybe we don't have a first derivative, plus, oh, I don't know, 19y equals 0. So our coefficient on the first derivative was 0. This is a 4th order linear because all of my powers of y are to the first power and all my derivatives are to the first power. We don't have something like that where I raise a derivative to a power. Those are incredibly difficult. We didn't even tackle those in this class. Homogeneous, because we have a 0 over here, it's set equal to 0 and with constant coefficients. Okay, so because of the linearity of the derivative operator, the derivative is a linear operator, meaning it distributes over sums and you can pull out constants. The derivative with respect to x of something like c times f plus d times g, where c and d are coefficients, constants, f and g are functions. Maybe I shouldn't, I don't want to use the letter D there. I don't know, let's call it K. The derivative is a linear operator. It can be distributed and constants can be pulled out. This would be derivative of f plus k derivative of g. You can distribute a derivative over sums and differences, and you can pull constants out. Because of that, this is an important theorem. If f and g are solutions, or let's call them y1 and y2, to an nth order linear homogeneous DE, then C1 y1 plus C2 y2 is also a solution. If you know two solutions to a linear homogeneous DE, whether it has constant coefficients or not, if you know two solutions, adding them together is another solution. Multiplying either of them by a number is another solution. So, for example, y double prime minus 8y prime plus 15 equals 0. I claim, we won't prove it right now, but I claim y1 equals e to the 3x is a solution. I also claim y2 equals e to the 5x is also a solution. You could check these. Pretty easy to check. Both of those are solutions to this DE. Then any linear combination of them is also a solution. I'm going to write that. Any linear combination remember, in general, DEs have an infinite number of solutions. And what I mean by any linear combination, any multiple of this one plus any multiple of this one is also a solution. So, I don't know, I could say y equals 7 e to the 3x plus 9, or even minus 9 e to the 5x is a solution to this DE. Check it. Like, not right this minute, but go home, check it. Try it on your own. Oh, everything I said was a lie. I was missing a y there. I need a y. Now, that's the DE I meant to write. Now, these two are solutions. That is also a solution. Any combination. So if we know two solutions, we can add them together and get another solution. Our goal is to find the general solution. To find the general solution, we need linearly independent solutions. So let's talk about linear independence. So if you've had any kind of matrix theory or linear algebra, then you know about bases and linear independent sets. If you haven't, I'm going to teach you basically some linear algebra right now that you need to know for this class. And this says if you have a set of functions, y1, y2, y3, up to say yn, is linearly independent if every linear combination yn equals 0 implies all the coefficients must be 0. If it's possible for you to write down a linear combination in general with arbitrary coefficients equal to 0, that must imply every coefficient is 0. Another way of saying this, linearly independent, means what this really means is you can't write one as a linear excuse me, combination of any of the others. It's impossible to write any one of these as a linear combination of the others. So to understand linear independence, you have to understand linear dependence. Consider this set. This set of functions, x, x squared, and 3x plus 4x squared. Let's call those, I don't know, y1, y2, y3. This set is linearly dependent. That's bad. We don't want dependence. We want independence. Why is it dependent? Because this guy is really just those two combined together. Y3 is just a combination of 1 and 2. It's 3 times the first one plus 4 times the second one. That makes this set linearly independent or linearly dependent. Dependent is bad. This set, the ones we had before, e to the 3x and e to the 5x, is independent. That's the good one. It's impossible to multiply one of these by a number and get the other one. You can't say, if we call this y1 and y2, you can't say y1 is just some constant 7 times y2. No matter what number you put there, it's not going to work. Or another way of saying that is if you know C1 e to the 3x plus C2 e to the 5x, if you know that must be equal to 0, the only way that's possible is both of the coefficients must be 0. This is a linearly independent set. What that means is, if we think of vectors in some vector space, these two, this vector is not some scalar multiple of this vector. They point at different angles. Hey, why do we care about this? Because another theorem. If we have, so given an nth order linear homogeneous DE, I'm trying to think how I want to say this. The general solution will look like y equals C1 y1 plus all the way up to Cn yn, where this set y1 up to yn are all solutions, and they're linearly independent. So if we have an nth order linear homogeneous DE, we need to go through the work of finding n solutions that are linearly independent from each other. And then we tack them all together and we get the general solution, the one that covers every possible solution. So that's our goal. Somebody hands us a 7th order linear homogeneous, we need to go through the work of finding 7 different solutions. Okay, now how do we check for linear independence? Because using the definition is an incredibly difficult way to check. I mean, that's the definition of being linearly independent, but that's not the way you check. We use what's called the Wronskian. This checks for independence. So we have some set of functions, say y1 up to yn. We build this matrix and we take the determinant of it. So we put on our top row all of our functions. In the next row, we put all their derivatives. All the way down until we build a square matrix. Remember, you can only take the determinant of a square matrix. So I need n rows since I have n columns. So this will be to the n minus 1th derivative. Then this is a matrix that we're taking the determinant of. So you're going to have to brush up on taking determinants of matrices. Once we get this determinant, this will equal some function. If that function is not identically 0, we have a linearly independent set. So if the Wronskian of this set, y1 up to yn, equals 0, the set is dependent. If it does not equal 0, the set is linearly independent. Okay, let's do a quick example. Let's do that one I was talking about before. It's going to be a nasty determinant because it's 3 by 3. So I had my set x squared, and 3x plus 4x squared. I called that y1, y2, and y3. So the Wronskian will be the determinant of, first in the top row, we put our 3 functions. Then I take derivatives. My suggestion is go down. Don't go row by row. Take a derivative, take another derivative. Take a derivative, take another derivative, and so forth. This would be what? 3 plus 8x. This would be 8. Okay, we need to take this guy's determinant, a 3 by 3 determinant. So I'm going to do what's called expanding across the top row. So this will equal, first I take this guy, and in my mind, cross out his row and his column. So x, I wrote down that guy, times the determinant of these 4 guys that are left over. So I've crossed out this row and this column. I'm looking at this 2 by 2 submatrix here. And we go multiply minus multiply. Kind of like cross multiplying. Down this way minus down that way. So we're going to need a lot of grouping symbols here. That one I can just do 2x times 8 would be 16x minus this one times that one. Okay, that's my first element here, or my first piece. Then I move across. I'm expanding across the top row, so now I move on to this guy. Now remember with determinants, it goes plus, minus, plus. Plus that one, minus, plus. If this were a 20 by 20, it would just keep alternating. Plus, minus, and so forth. So minus, I'll try to write it all in one line. That guy. Now in our minds, we cross out this row up here, this column, and we take the determinant of these four. 2, 3, 4. And we go that way minus that way. So 1 times 8, 8, minus that guy times that guy, 0. Then we move on to the next one. Remember, it goes plus, minus, plus. So plus, minus, plus, that next element. So in our minds, we're crossing out this row and this column, and we're looking at these four. And we're going to go down, minus, down. 2 minus 0. Okay, now let's just clean everything up and see what we get. So I'm going to get 16x squared minus 6 minus 16x minus 8x squared plus 6x plus 8x squared. Wait, did I screw something up? Let me pause just a second. Okay, the mistake was right here. Let's clean this up first. So this would be 16x minus 6 minus 16x minus 8x squared. Distributing here, plus 6x plus 8x squared. These two cancel. I get negative 6x and 6x, negative 8x squared and 8x squared. We get 0. This set is linearly dependent. That's the bad one. Okay,